The next portion of this chapter takes a look at how we deal with capacitors that are arranged in our circuit. We're going to start with parallel capacitors. Remember from the last unit that capacitors are the way that charge is stored in a circuit. And when we have parallel capacitors, what we find is that the total charge supplied by the current is distributed among all the capacitors. So the total charge is equal to the charge from capacitor 1 plus the charge from capacitor 2 plus the charge from capacitor 3. The potential across each of the capacitors when they're arranged in parallel is the same. And we remember again from our last unit that charge equals capacitance times the voltage or the potential. So our equivalent capacitance is equal to the sum of each of the capacitors. So let's take a look at a problem that has a couple of capacitors that are arranged in parallel and see if we can figure out what the equivalent capacitance is and what is the charge that's stored on each capacitor. Again, because they're in parallel, all we have to do is add them. So the equivalent capacitance is simply 20 microfarads plus 30 microfarads, and we get 50 microfarads. That's pretty easy. What's the charge on each capacitor? Well, from our equation from the last unit, charge is equal to capacitance times voltage. So the charge for the 20 microfarad times the 12 volts, and we get 240 microcoulombs. The charge for the 30 ohm, charge for the 30 microfarad capacitor is going to be 30 microfarads times the 12 volt power supply, and so we get 360 microcoulombs. What happens when we put capacitors in series? Well, the arrangement is shown, and the charge from the power supply first encounters the first capacitor, or we could call it C1, and it charges this capacitor. That capacitor in turn repels an equal quantity of charge in the next capacitor, and it works that way through each of the capacitors in series. So for capacitors in series, the total charge equals the charge on capacitor 1, which equals the charge on capacitor 2, which equals the charge on capacitor 3. Since the potential difference from one side of the capacitor series to the other, here it's represented as A and D, must be the voltage created by our power supply. So the potential difference from point A to point D equals the total voltage in my circuit, then V1 plus V2 plus V3 must equal the total voltage. So similarly to resistors, 1 over the equivalent capacitance equals 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3. Then when I do that, I have to remember to take the inverse so that I can get the equivalent capacitance. So series capacitors are similar to parallel resistors. If you can remember one set and know the other is flipped, then that will help you keep track of how to do each type of problem. Let's work through capacitors arranged in series. We have the same 20 microfarad and 30 microfarad capacitor arranged in series, same 12 volt battery. Let's find the equivalent capacitance of the circuit first. So 1 over the equivalent capacitance equals 1 over 30 plus 1 over 20. Well, we can change that to 60, so we've got 2 over 60 plus 3 over 60 equals 5 over 60. Capacitance, equivalent capacitance is the inverse of that, so that's 60 over 5, or 12 microfarads. Charge on each capacitor, on the 20 microfarad, it's going to equal the charge on the 30 microfarad, which equals, in this case, the equivalent capacitance, 12 microfarads, times the total voltage. So we get 144 microcoulombs. What is the voltage across each capacitor? Voltage across the 20 microfarad capacitor is just going to be the charge, 144 microcoulombs, divided by the capacitance, 20 microfarads, and I get 7.2 volts. The voltage across the 30 microfarad capacitor, same charge, 144 microcoulombs, divided now by the 30 microfarad capacitor, and I get 4.8 volts. My voltage across each capacitor should add up to 12 volts, which it does. So how do I deal with circuits that have resistors and capacitors? They're called RC circuits, and to draw them, it's going to look like this. So here's my power supply. The current is going to go this way through my circuit, so it's going to hit the capacitor first. So the current first hits the capacitor and charges it. As I charge the capacitor, then the potential difference for the capacitor reaches that of the power supply. When that happens, the current stops flowing. So if I look at the graph of voltage versus time, what I'm going to see is I start out with no voltage across the capacitor, and then as time goes on, the voltage builds, and then eventually levels off at the voltage of my power supply, or the EMF. So as the capacitor gets charged and builds up a potential difference, the current through the circuit decreases, and so my EMF, or the total voltage, is going to be current through the circuit times the resistance of the resistor plus the charge on the capacitor divided by the capacitance. And since the current and the voltage are continually changing until the capacitor is charged, it's a log equation. Okay, so V in this case is the voltage across the capacitor, and the E is the battery EMF. Here we have the same type of circuit as illustrated before, and if we take a look at what happens when we close the switch, right now we have a 30 kilo ohm resistor and a 40 nanofarad capacitor. When I close the switch, what I'm going to see is the current across the resistor. So as time goes on, the current decreases. I can also look at what happens to the voltage across the capacitor when I close the switch and allow the current to flow. So as time goes on, the voltage across the capacitor builds up. Let's take a look now at what happens when I have a circuit that just has a resistor and a capacitor, but no power supply. Capacitor is charged, so it is full of electrons that have a reasonable amount of energy, so this is where our energy is going to come from. When I close the switch, the capacitor will discharge, and that provides the current through the resistor until the capacitor has drained all of its charge. And so that is what this graph is showing us, that we start out with some non-zero voltage in the capacitor, and then when I close the switch and allow the circuit to be complete, the charge drains from the capacitor, and as the charge drains, then the voltage drops. Let's take a look at an RC circuit problem. First, we're going to look at the initial current. Remember, when we first close the switch and the capacitor is uncharged, there is current flowing through the circuit. So we treat it as just a regular circuit problem without the capacitor in it. So our current is simply the voltage divided by the resistance, and that gives us 0.6 amps. And that's our initial current, because as the capacitor gets charged, if you remember what happens to the current, it will change. Final current, once the capacitor is charged, is 0. When the capacitor is charged, what charge does it hold? Well, charge is capacitance times voltage. Our capacitance is 30 millifarads, and our EMF is 12 volts. So we get 360 millicoulombs. So what happens when we put resistors and capacitors in parallel? We allow the circuit to reach equilibrium, and at equilibrium with the capacitor, the current through each branch is 0. So the total current is equal to the sum of the currents in each branch, which is equal to 0. Voltage is still present because voltage across the capacitor is going to be the same as the voltage across each resistor. And the voltage across each branch is simply going to be the voltage of the capacitor, which is the charge divided by the capacitance. So let's take a look at an example using this information. So we have an EMF of 6 volts, resistor 1 is 20 ohms, resistor 2 is 30 ohms, and our capacitance is 4 microfarads. And we want to find out how much total current is passing through the circuit. For our resistors, we want to find out the equivalent resistance. So 20 and 30, common denominator is 60, so we have 3 over 60 plus 2 over 60, and that equals 5 over 60. So our equivalent resistance is 60 over 5, or 12 ohms. So our total current initially is going to be our 6 volts divided by 12 ohms, or 0.5 amps. How much current is passing through each resistor? Well, I have 6 volts across each resistor, so current 1 through resistor 1 is just going to be that 6 volts divided by the resistance of 20 ohms, and I get 0.3 amps. The current through resistor 2 is just, again, that 6 volts divided by its resistance of 30 ohms, and I get 0.2 amps. So the current through each of the branches add together, I get my 0.5 amps, which is as it should be. How much charge can the capacitor store when the circuit is at equilibrium? Well, charge is capacitance times voltage. So I have 4 microfarads times 6 volts, and so we have 24 microcoulombs is our charge. And that's some simple examples of RC circuits. We have to break it apart and do the resistor part and the capacitance part, and remember that it doesn't happen all at once, and as time goes on, the system changes.